All right. So this is a band structure of a real metal, aluminum, and this is the Fermi energy. And so therefore, those bands which are within a range of energy kBT around the Fermi energy, those will be affected at a temperature T. That is the region where this del F del epsilon term will be significant. So those bands, so if I look at this band, for example, this would be completely filled, right, at room temperatures. So therefore, this will not contribute to the electric current. Only those bands which are within, which have states within an energy range of kBT around the Fermi energy, are the ones that will contribute. So what we argued earlier, that completely filled bands do not contribute to current, remains true in this case also, and it sort of shows up through this derivative of the Fermi function. And to order kBt squared, I can write this derivative to be a delta function. I mean, at low temperatures, it is a delta function at T equal to 0. But even at low temperatures, up to order kBt square, I can replace this by a delta function. So if I replace this by delta function, delta epsilon minus EF, EF being the Fermi energy, then I can just take this tau at the Fermi energy, and then so there's a little bit of algebra here, so I'm just trying to spell that out. So you write, instead of tau at epsilon k, you write tau epsilon f, and that can be pulled out of this k integral, and the remaining terms, you have one v, another v, and del f del epsilon. So that is, so one factor of v and del f del epsilon is being written in this way. So v is of course 1 over h cross del epsilon del k. Then you have del f del epsilon. So these two can be combined to write the k derivative of f, that something we had earlier. So then with that, this expression for sigma n now becomes e squared tau at epsilon f, k integral of v, and then this factor 1 over h cross del f del k. Now this integral, this k integral, can be performed. So it's a simple integration by parts. So you get, excuse me. So suppose v is the first function and this is the second function. So then this will be one term and that will be the other term. Now, when you take the limits at the boundaries, vkf, I mean, this is a periodic function. So when you are integrating this over the Brillouin zone, it becomes 0. So you are left with only the second term here, del v del k f. And this del v del k, of course, now v is del epsilon del k with a factor of 1 over h cross. So so essentially you'll be left with this factor of m inverse, the effective mass tensor, because you'll pick up two derivatives, the second derivative of epsilon from this del v del k term with respect to k, which is inverse of the mass effective mass tensor. Okay, so what we got is that the DC electrical conductivity can be written in terms of inverse of the effective mass tensor also, or its derivative over this thing. So what we have written here is, suppose we are at really at 0t, then if this factor of f can be omitted and I can just take the integral over the occupied states. But of course, if you are at a finite temperature, then you have to uh, integrate this over the Brillouin zone also, and f will take care of which states are occupied and which are unoccupied. But now in this line, deliberately, we are assuming that we are at 0t or at very small temperatures. So the reason for that is that now I can argue that because m inverse, which is derivative of epsilon with respect to k, epsilon is a periodic function, so these derivatives are also periodic functions of k. So I can replace this integral. So in other words, integral of m inverse also over the entire Brillouin zone would give me 0 because it's a periodic function of k. So therefore, if I have partially filled bands, then I can equally write this to be, this expression for sigma to in terms of integrals over the occupied states, or I can just change the sign and write it in terms of the integrals over the unoccupied states. So we sort of recover the electron hole picture. We can equivalently use the electron picture or the hole picture. And that comes from the fact that this effective mass tensor is a periodic function. The last point I want to make here is that suppose we had free electrons, so then the dispersion, the dependence of epsilon on k would be of this form. And then this second derivative of epsilon would just be 1 over m delta ij. So if I have a real system, a real metal, let's say, in which M inverse has this form, where M inverse is a diagonal, and it has the same diagonal element everywhere, and is independent of k. So the same star is independent of k. So if I have a band structure which gives me M inverse to be of this form, then this conductivity tensor would reduce to a diagonal form where the diagonal elements such as this, exactly the Drude form. But that happens only when I have a band structure or band dispersion that looks like that. And that often do not happen in real materials. In some metals, which are very much free electron-like, you may have exactly or nearly exactly parabolic bands, which would give you diagonal structure for this M inverse, and then you can get a Drude-like formula like this. If it's in non-metals, of course, it doesn't happen. And there also something to remember is that this M star is a result of the band structure. So this relation need not be exactly, so this M in the band in the solid need not be equal to the free electron mass. It could be somewhat different. Okay, and similarly for unoccupied levels, if I have a structure for M inverse which is minus 1 over m star delta ij, then I can, in terms of the whole density, I can write sigma like this. But essentially, I can recover the Drude form only in such special cases, which may happen in metals, but typically will not happen in other systems. Okay, so that's about DC electrical conductivity. Now we'll go over to discussing AC electrical conductivity. Any questions at this point? All right. So in case of AC electrical conductivity, what we have, the external fields that we have, is we have a time-dependent electric field. Okay, and which is of this form. We are writing here one omega component. Of course, in general, electric field can involve many omegas, but we can look at each frequency component at a time. And so in the expression for G that we had, so let me just get back to that once again. Yeah, so this is the expression that we have. And in fact, this is the most general expression we had written, a T integral here, and then this, which involved the sort of external field and gradients in the system. And what we had argued is that, and that physical argument is important, is that we will take the time dependent, will not consider time dependent in this V, etc., when there are no magnetic fields. If the electric field is time dependent, of course, we have to take that into account, and the other time dependence is here, which we have to integrate over T primed. So this is the situation now we have. We have this factor which depends on time, and then we have an electric field which is explicitly time dependent, and of course grad mu and grad T, etc., are zero. So in that situation, I'm just writing G minus G naught here. So this is the part that comes from P. Okay, the probability of survival. Then I have del F del epsilon part, and then I have this V factor, and this is my E. Right. So then I have taken a particular time dependence of E, so which is written here. So this is E T primed. So then I can take this T primed dependence into this integral over here. After that, it's a simple integral over T primed, which you can easily perform. So I'll share these notes, and there's nothing very profound in this. You do the integral, you put the limits. I'm integrating from minus infinity to T. So eventually you get this expression in this line. Sorry. So this again will give me an expression for sigma. Okay, so what I have got here is the part of G that is in excess of the equilibrium distribution function. So then I have to multiply that by V, and then electric charge with a minus sign, and integrate over K. So that will give me the expression for sigma. So this is how I get sigma omega. Okay, here. K integral over this. Now, an interesting limit of this is sort of to understand the significance of this. So let us look at the limit when omega tau is much greater than 1. So we are talking of clean enough samples so that the relaxation time is large enough, and also the frequency is high so that this condition is satisfied. Omega tau is much greater than 1. So in that case, again, this is a bit of algebra which I leave for you to work out. So if you look at this factor, the omega dependence is right here, and So you will end up getting this as the leading order contribution to the AC conductivity. So this algebra and the subsequent things that I will discuss involve some bit of algebra. So obviously I cannot do those now, but in the next lecture, when we actually again go back to the board, if you have difficulty or something you found difficult to sort of follow, I'll work that out on the board. But I mean, what I want to tell you is that in this there is basically nothing that you cannot work out. I'm basically, this is the only part that has omega dependence. So you take this and work it out in the limit that omega tau is much larger than 1. That's as simple as that. And then to the leading order contribution would be this. There'll of course be, so this is the imaginary part of sigma. Of course there will be a real part which goes as 1 over omega squared tau squared, and the 1 over omega tau thing will give you this. So if you keep only the leading order contribution, this is what you will get. But before you arrive at this expression, you will get something which is, exactly like, Drude-like expression. So you can write this basically in terms of, so if you did not have this denominator here, what you have in the numerator, it just gives you the DC conductivity. So it is DC conductivity divided by omega tau, 1 over tau minus I omega, if you neglect the sort of K dependence of omega. So that's exactly what we got in Drude formalism also. The AC conductivity was the DC conductivity divided by 1 by tau minus I omega, exactly this factor. So you recover the Drude result, but in a much more general setting where the electrons are now in band states. They are not classical particles. But on the other hand, it's sort of interesting to think that sort of simple, naive approach like the Drude model did get a similar expression, at least the omega dependence. The other thing you get from here is that to the leading order, there'll be a peak in the AC conductivity as omega goes to 0. Now you do see this peak in real conductivity measurements, but it may not happen exactly at omega equal to 0, but there is a low frequency peak. Omega, at some omega you do have a peak, which is sort of called the Drude peak. All right. Now we get to the discussion of thermal conductivity, how to calculate thermal conductivity. So what we will do here is we'll try to evaluate thermal conductivity of a metal. This will be, all these discussions are relevant to the metals because of some of the approximations that we have made. So now we'll calculate thermal conductivity, and eventually we will recover the Weidemann's-Franz law from a more general setting of these band electrons. So what we are doing here is, so I have a metallic system, and there is some region in it that I'm considering where the temperature is T, right? So if heat is being generated or coming in that region, that has to be balanced somehow so that the temperature remains constant in this region. So from thermodynamics, this heat generated or heat coming into that region has to be balanced by this flow of entropy at that temperature T. Now this TdS again from thermodynamics is just du plus pdv minus mu dn. Okay. Now, so these dAs, du, dv, dn, etc., of course, are changes in the system. So these can be related to the flow of these quantities. So du can be related to the, du is what? It's the internal energy. So change in internal energy can be related to the flow of energy in that system, in that region. dV, of course, is zero because the volume of the metal as a whole, or for that matter, that small region, is not changing. So dV will be zero. And there could be dN. Electrons could be coming in, going out, and so on. So dN could be related to the number current, the number of electrons flowing. And then JQ is the heat current. Okay, the heat energy flowing would be related to the entropy current, called that JS. So JQ is the same as TJS, where JQ is the heat current and JS is the entropy current. dV is zero, so we simply have TdS equal to du minus mu dn here. So we, as I said, we relate these to the current. So TJDS, I can write TJS will be equal to J epsilon, which is the sort of energy current, internal energy of the electrons, minus mu Jn, where Jn is the number current, simply the number of electrons flowing, or that current density. So from this thermodynamic relation, I can write this relation, in what I marked as equation 40, in terms of the currents of entropy, the internal energy, and the number of electrons. And remember, the internal energy is simply the band energy of the electrons. There is no other energy. Everything is captured in the band electrons, the band energies. Okay, so as I said, these J's are various currents. So now I can write these currents in terms of integrals over Brillouin zone of various quantities. So the energy current, the internal energy current, as I said, is simply epsilon. This is for the nth band, epsilon at some k, vk, and the distribution function summed over all bands. Similarly, the number current will simply be integral over the velocity and the distribution function. And this JQ then, okay, so the JQ then would be, I haven't written the expression for Jn, but Jn would simply be an integral over, oh, sorry, I have written here. Equation 42 is the number current, which is simply the integral over V and G. So now I plug these two expressions in equation 40. So J epsilon involves an epsilon, and there is a mu Jn thing here. So when I put those in and take the difference, I can write JQ, which is the left-hand side here. The JQ turns out to be integral over K epsilon minus mu Vn Gn. Now, Gn is the same non-equilibrium distribution function that we have derived. And so we will take a situation where H is zero, there is no magnetic field. Of course, there is a temperature gradient, and in general, there is an electric field, a uniform electric field. So that is the situation we are considering. now. Okay. The next, this thing is, so see, there are these two terms, E times the electric field and then the grad mu. Now, in the subsequent discussions, we'll combine these two. So I'll define a quantity electric field plus grad mu over small e, and we'll call that F. So I have written it somewhere. Yeah. So this is how F is defined, which is electric field plus grad mu over E. So in terms of that F, G can now be written in this way. Nothing has changed. I've just defined this quantity F in this way. And subsequently, we'll write everything in terms of this F. Okay. So once I have written G like that, I now calculate the electric current, the charge current. The charge current, of course, is this. We have written this several times. So this is the charge current. And now we plug in this this part of V, the non-equilibrium part of V, in this integral for G, to write this like this. So there is this factor of tau, derivative of F, V, that comes from G. Then there is another factor of G that comes from here. And then this factor within these brackets. So that is it. So now I separate this out into two terms, one depending on F, the other depending on grad T. Earlier we did not consider grad T, but now we have grad T. So it's just simple algebra. I write this in two terms. So this is the term that depends on F, and the second term that depends on grad V. After this, there is some, some notation algebra which I cannot work out totally today. So as I said, I'll come back to this next time. But I just want to give you the logic that one is following here. Apart from that, it's just some notation and algebra. So there's nothing again fundamental about it. So this thing conventionally is written like this. So everything that multiplies F is written as L11, and everything that multiplies grad T, the temperature gradient, or minus grad T, is written as L12. So you just write that. That's it. Okay. So just to remind you, I write JQ. We had written this expression for JQ earlier. So it's the same expression. JQ as J epsilon minus mu Jn. So that is that expression. Now again, I write J in JQ again, I put in the non-equilibrium expression, the non-equilibrium part of G, the distribution function. So here, so this part. So when you put that in, you again get two terms. One depends on F, the other depends on grad T. So when you work the algebra out, you will get this term coming from F and this part coming from grad T. Okay. So as before, we introduced these notations. So everything that multiplies F here is called L21, and everything that multiplies grad T is called L22. Now define some quantity called, or quantities called curly L, and in a few minutes it will become clear why they are useful. So that this L11, which was, oops, L11, which was integral over along with this factor of E squared, integral over del F del epsilon tau and two factors of V, that is defined as curly L0. L21, which is T times L12. I have better expressions for this. Yeah. So I have written these once again here. So this was L11, del F del epsilon tau and two factors of V. This is L12, which was del F del epsilon tau, two factors of V along with this. And L21 was exactly as L12, except that 1 over T was missing. I mean, when you work the algebra out, this is what you'll find. It just doesn't have that factor of 1 over T. Otherwise, it's same. And L22 was this squared, epsilon minus mu squared over T. Otherwise, all the other factors are same as L21 and L12. So then one introduced these notations, curly L0, curly L1, curly L2, and L21 is the same as T times L12, obviously. That is defined as 1 over E L12, and L22 is defined as 1 over E squared T L22. We haven't yet well, L naught is defined by this. We'll just write a more general compact relation or expression for this curly L's now. So that is what I have written here. Before that, this sigma, if you look at your expression of sigma, it involved E squared tau. So just open your expression for the DC conductivity sigma. It was E squared, then integral over the Brillouin zone, then tau, then two factors of V and del F del epsilon. Okay? Now that del F del epsilon is of course significant, as we argued, only near the Fermi energy. Okay. So this expression, this equation 50, is sort of bit of a order of magnitude argument is involved here. So we know that del F del epsilon is non-zero, only close to epsilon F. So therefore, we replace that by a delta function. We can replace that by a delta function. But then we are not writing that delta function as epsilon minus epsilon F here really. We're just writing epsilon minus epsilon K, but keeping in mind that this quantity, delta epsilon, sigma epsilon, the DC conductivity, is essentially the same as its value at when epsilon is equal to the Fermi energy. In other words, it doesn't have a very strong energy dependence. So that is something we sort of argue, and because of that, the del F del epsilon is written as a delta function like epsilon minus epsilon k in the expression for sigma. Then you have two factors of V, and this epsilon, this tau has also been pulled out of the integral. We can put tau at epsilon f. So the reason we do that is that then in terms of this epsilon, this sigma, I'm sorry, the L alphas, so I have a L0, I have a L1, and I have a L2. So the L's can in general be written as this. So that was the purpose of defining that way, the sigma. So L alpha basically involves an integral over the alphath power of epsilon minus mu. And then there is a factor of sigma and del f del epsilon. Okay. All right. So then what we do? We write this expression for sigma that we wrote here in equation 50. We just put that in this one over here. So then I pick up this. There was this e squared, there was this tau, then there was a delta function, two factors of v. And from the definition of L, I have the other things. Then energy integral, k integral comes from sigma, and there is a del f del epsilon. Okay, so this delta function would give me del f del epsilon at some k, and then I have to integrate it over the Brillouin zone. There is a tau, and there is this power of epsilon minus mu alpha. Okay, so with that definition for curly L alpha, again I have written it here. So this is my curly L alpha for alpha equal to 0 and 1 and 2. Now after this, how to evaluate this alpha 0, alpha 1, alpha 2 is something that will involve the Sommerfeld expansion that we talked about while we were doing the Sommerfeld model. I want to go through it a bit, but not today, in the next class. So what I'll do is, I'll tell you what you get after you go through the exercise, which as I show you, I'll show you the outline in the next class. So L11 is simple to evaluate. Let us check what L11 was. L11 was simply curly L0, so which doesn't have a factor of epsilon minus mu. Alpha is 0 here. So it will simply turn out to be, and remembering that this derivative of the Fermi function is significant only near the Fermi energy. So you can write L11. Let me enlarge it a bit. You can write L11. You'll get L11 simply to be equal to the DC conductivity at the Fermi energy. Fine. If you evaluate L21 and L12, you can show that they are, to some factors of kBt squared and other constants, they come out to be proportional to sigma primed. Okay, L21 and T times L12, they are equal to some constant times sigma primed. The sigma primed is the derivative of the DC conductivity at the Fermi energy, and L22 is Kb squared T over E squared times again sigma at the Fermi energy. So these are the basic results. So these expressions for these quantities L11, L21, L12, etc., L22. So these allow you to calculate the heat current, the energy current, etc. I mean, all these quantities, the electric current, everything. Once you know these quantities, you can calculate all these currents, and everything is expressed in terms of the DC electrical conductivity or its derivative at the Fermi energy. Now, having learned that, let us try to see if you can calculate thermal conductivity. Now, thermal conductivity, of course, relates flow of thermal current, that is heat current, when there is a temperature gradient in the system. Now, remember what we argued earlier when we were studying the Drude model. Where were we? Yeah. So, why is it disappearing? Oops. Any idea why it is disappearing? Ah, now it comes. Okay, suppose we have a system situation like that. There are two temperatures are maintained at the two ends of a metallic rod or something, and so that sets up a temperature gradient. When the temperature gradient is initially set up, of course, there will be flow of electrons from the high temperature region to the low temperature regions, which could set up a charge current. But eventually, because we are in an open circuit situation, so there's nothing connecting this to this by a conductor, so that will build up an electric field which will resist that motion. So eventually, we'll only have an energy current, heat current, and not a charge current. So in that steady state, we have to look at the system. So the charge current is 0. So what was our expression for charge current? Here. So we wrote charge current J in terms of these quantities L11 and L12 and F and grad T. So if you put J equal to 0, so what we'll have is L12 times this grad T is equal to minus L11 F. Or rather, F is equal to this. So that is the condition for the charge current to be 0. So now let us see what these are. What more can we do from here? Okay. So with that, so this is the condition for the charge current to be 0. F has to be equal to this L11 inverse times L12 times grad T. And then we want to put that in. So we will put that expression for F in the expression for this heat current. And then if we get heat current to be proportional to the temperature gradient, then whatever the proportionality constant is my thermal conductivity. Okay, so I take this expression for JQ, and in this expression, I put in place of F, I put this in terms of grad T, which is the condition for the charge current to be 0. That's exactly what we did when we did the Drude model. So you plug this in the expression for JQ. So you will get these two terms. So here in the first term, I have put replaced F in terms of grad T. So eventually you will get this. So this factor multiplying grad T. So I have got something that is proportional to grad T, JQ proportional to grad T. So this proportionality constant these terms in the bracket will give me the thermal conductivity of the material. So now let us see what these are once again: L22, L12, L11, etc. So L11 is proportional to or exactly equal to sigma at the Fermi energy. L12, L22, these are L12, L22, these are proportional to sigma primed, and L22 again is proportional to sigma. So L22 is proportional to sigma, L12, L21, these are proportional to sigma primed. Now, as we argued earlier, sigma is not a strong function, is not a doesn't have a strong dependence on energy. So close to Fermi energy, it's essentially what it is at Fermi energy. So any variation is at least smaller by sigma over epsilon f. So the order of magnitude of sigma primed would be sigma over epsilon f. Okay. So using that, let us, I have it somewhere here. So if you, what I just said, if you work this out, you will get sigma 22 to be proportional to L22 to be proportional to sigma, L12, L21 is proportional to sigma primed, and the argument now is that sigma primed goes as sigma over epsilon f. It's not bigger than that. So the factor, one of the factors in the expression for JQ, which involved this L21, L11 inverse and L12, will now go like, so in place of L21, so this is, right. So sigma primed times over epsilon f, and there was a kBt squared factor. Then L11 inverse is 1 over sigma, and L12 will give you this other factor, kBt squared over T, epsilon over epsilon f. So everything combined will give you sigma times kBt over epsilon, or that is Fermi energy squared. Again, if we are at low temperatures, and we are at low temperatures, this is a small quantity. kBt over epsilon f is a small quantity, at least 10 to the minus 4 or smaller. So therefore, in this expression, this term is much smaller compared to L22, which goes as sigma. So I can keep only the L22 term, which is proportional to sigma. And so when I write this k, then k will turn out to be proportional to sigma. And that's exactly what the Wiedemann-Franz law is. So putting all the factors in, what you will get is here. So K, the thermal conductivity tensor, this is also now a tensor because it is simply proportional to sigma. Sigma is a tensor, so this one also is a tensor, is some constant times T times sigma. So this constant, in the Rude model, we had got this to be 3 by 2. Here it is pi squared by 3. Apart from that, the factor of kb over e squared t, these are exactly the same. So what is interesting and sort of remarkable is that this result, which comes out of a more detailed and realistic calculation of electrons living in periodic potentials of the ions, we got the same result in a Drude model in a purely classical picture. But nevertheless, you do recover the Wiedemann-Franz law here also, and you know what the proportionality is. So that's all I can do today, because as I said, I cannot do the algebra. So we'll start from there, and I'll try to explain this a little better. I'll share these notes with you. There's a little bit of more algebra involved than what we saw so far, but not a great deal. So which with these notes you should be able to work it out. But again, as I said, in particularly in condensed matter, at every step there are assumptions that we take something to be of order this, we replace del epsilon by some delta function. So why one is doing that, where one can do that, where that breaks down, or where the t dependence is taken, where it is not taken, and in what situations those are justified. These are some of the subtle arguments which are much harder to get. Once you get that, the algebra just follows. There's nothing sort of difficult about that. But to get that is the tricky part. So I would ask you to focus on that. So, are there any questions?